Okay, so this is a video to look at the last thermodynamic terms in the A2 Module 1 specification. So we're going to look today, first of all, at delta S, which is the entropy, as you can see on the screen in front of you. And then when we're finished that, we're going to move on to look at the delta G. The delta G is called the Gibbs free energy, but we'll get there in a short while. So let's look at our delta S first and what it is, how we look at it qualitatively, and then we'll look at how we look at it quantitatively, or in other words, how we actually calculate out this value. So this topic that we're moving on to now really allows us to predict whether a reaction will or will not be spontaneous. In other words, will it happen without some sort of external force being added to it. Okay, now we probably think about exothermic reactions, so reactions that give out energy as being spontaneous and just happening without any particular input of energy. But we'll also be aware of a lot of endothermic reactions which also occur spontaneously. So there's a few below that I'm going to show you now. I'm not going to talk too much about them, but you can see that they're endothermic reactions and they all happen spontaneously. I suppose the most simple one is that ice melting at room temperature requires 6 kilojoules of energy per mole of ice, but nonetheless still happens at room temperature. We don't need to give it any particular input of energy or input of force. Expansion of gases, dissolving this ammonium nitrate we have there, and then an acid-base reaction between a carbonate ion and a hydrogen ion requires quite a significant input of energy. You can see the last one there, but nonetheless it still occurs spontaneously at room temperature. So my point here is that exothermic reactions and endothermic reactions both occur spontaneously, so we can't use the term delta H to decide whether a reaction does or does not occur spontaneously. So there must be some other driving force, some other thermodynamic term that predicts whether a reaction is spontaneous or not. And that's where our entropy, or S, or entropy change, and then leading into our Gibbs free energy later today, come into play. So let's have a look. So how could an endothermic process be spontaneous? So as I said in the previous slide, there must be something other than delta H that must control this energetic feasibility of a process. And that other thermodynamic term is indeed the entropy, shorthand S. So enthalpy is H, entropy is S. Now how do we measure entropy of a system? Well, this is a really easy concept to get your head around at A level. It is essentially a measure of disorder. Okay, so it's a measure of the randomness of the molecules in a system. Okay, and it's a measure of the dispersal of the energy in the molecules of a system. Now, if I was to sort of maybe use the good old analogy that many chemistry teachers will use, which is after your mum, your dad, or maybe even yourself, who knows, tidy your bedroom. Everything is sitting in nice piles, everything's tidied away. After about a week or two, it's all over the place. Clothes are everywhere, food probably sitting beside your bedside, okay, any toys that you might have, or games or whatever, all over the place, okay. So you have gone from a very ordered bedroom, which has a very low entropy, to a bedroom where everything is randomly dispersed, and now you have a bedroom which has got what we would call high entropy, or a high level of disorder. And that's as simple a way as you can probably think of entropy, as just a level, or sorry, a measure of disorder. Okay, and that disorder can come from the randomness of molecules and from the dispersal of energy. So how do we increase this disorder? Well, we increase it by putting more particles in, more molecules in. And that would stand if you had more clothes, or more computer games, or more bottles of Diet Coke or whatever lying around your room. You'll have more disorder. If the temperature was increased in your room, so let's pretend that you put so much heat in those particles can actually start to move and vibrate even more, those clothes and bottles and games and so on and so forth. So that increases the disorder even further. And if you made your room so warm that everything actually turned into a gas, those particles would be even more disordered and would have an even higher entropy. So we basically make the positive correlation between entropy and disorder. Okay, now then we talk about delta S, and delta S is the change in entropy. So if you could measure the change in disorder of your nice tidy bedroom to your really, really untidy bedroom, okay, that change in disorder would be your delta S. Now, how would you do that? Well, you would need to have a measure of the order or disorder to begin with, and you'd need to have a measure for it at the end. And that's exactly what we do in a chemical body, a chemical reaction. It's the same thing. So the delta S is the change in disorder within the system arising from the reactants changing into products. In other words, arising from your nice tidy clothes arranged to your bedroom, which is a mess, within a week or two. So we're going to look at the next page over here, and we're going to look at just being able to predict qualitatively, no numbers, no values, nothing involved, no calculations. What will we have here? Will we have an increase in disorder? Will we have a decrease in disorder? Or does disorder stay the same? So I'm going to talk you through this one, then you're going to do the next slide over. Just when we go to the next slide, just pause it and do it, and then check your answers. I will continue on talking and do the answers. Okay, so what are we looking at here? How do we measure disorder? Well, on the left hand side we have two gases, on the right hand side we have liquid. So I'm already thinking there's a decrease in entropy here. Okay, so, oh, no I'm not. I'm thinking there's an increase. No, I'm thinking there's a decrease in entropy. So this system becomes more ordered. Okay, we also have to take into consideration how many particles, and we have on this side 3, 2. So we 3 gas going to 2 liquid, so there's definitely a more ordered system, or a decrease in disorder. So entropy will decrease there. You would get a negative a negative value for your entropy, for your delta S. So we'll just write that beside here. Delta S would be negative. Let's go to the next one. So what am I looking for? So solid and aqueous, they're pretty ordered. Solid is very ordered, aqueous not so much. On the right hand side then we have aqueous, liquid and gas. So our solid has gone. Let's check particles. We have 1 and 2, obviously 3 on that side and 3 on that side. So there's definitely here an increase in disorder, and we would have a positive delta S this time. Let's go to C then. So C, we have solid and gas, and we have 3 particles. Let's go to the right. We only have solid and we have 2. So there we go. That's definitely a much more ordered system. So we would have a decrease in delta S. Delta S will be negative in this context. Okay, let's look at this one. We have solid, solid, and we have 3 particles. On the right hand side we have solid, gas and liquid. Okay, so we've 4 particles, and so 3 to 4, and solids going to gases. Again, that's an increase in your delta S, and your delta S this time will be positive. So that's how you work it out qualitatively. Alright, so I'm going to go to the next slide over, and then it's your turn. So you've got a variety of ones there, so have a look down them. You've got 3 options. You have an increase, a decrease, or remains approximately constant. So pause the video now, have a look at them, and then I will give you the answers. So the first one's a solid coming out of solution. Okay, so that is a decrease. It's becoming much more ordered. A solid melting, becoming much more disordered. That's an increase. Solid subliming is an increase also. Number 3, that's a big increase. 2 liquids mixing together probably doesn't change very much. 2 liquids mixing together, they're both liquids before and after. Number 3, we have a solid, or number 5, sorry, we have a solid turning into a solid and a gas. 1 molecule going to 2, so we have a big increase in disorder there. Number 6, we have water, liquid water turning into 2 gas molecules. That's a big increase in disorder. Number 7 is the opposite to number 6, so it's a big decrease in disorder. Gas is going to liquid. Number 8, we have 2 molecules turning into 1, so you probably have they're all in solution or liquid, so you'll have a bit of a decrease in disorder there. And number 8, you have 2 moles of gas. Number 9, sorry, you have 2 moles of gas on the left, 2 moles of gas on the right. So that's probably going to remain approximately constant. Okay, so delta S values have to be calculated. So we're not going to get away with just doing qualitative appreciation or treatment of our delta S. We're going to have to actually calculate these values out. And S, or entropy, is measured in joules. Now this is where we need to be a little bit careful, for especially for what comes later, because what comes later will be using delta S, but it will be using it with delta H and delta G, which are both in kilojoules. So we need, when we do that, to turn our delta S into kilojoules. Alright, and that is simply joules to kilojoules, you should know, is divided by 1,000. But you'd be amazed how many people forget to do that in an exam. So these are the units of entropy, and what they basically mean is how many joules, which is a unit of energy, are needed to raise 1 mole of a substance by 1 Kelvin, okay, which is a temperature. Okay, right, this is a really important formula at the bottom of the page. This is how you actually work out your delta S, your entropy change, and it is the sum of the entropy of all the products minus the sum of the entropy of all the reactants. Very simple. I'm going to do 2 worked examples on the next page over, and then you're going to do, so maybe I'll do one and you can pause the video for the second one and have a go at it yourself just to check that you are correct. So I would copy that equation that's on the board down now before I move on. I'll move on in 3 seconds. 3, 2, 1. So we've got 3 questions to do here. We've been asked in part A to predict qualitatively what we should find with our entropy change. So we'll do the same as we've already done. So we've 4 gases on the left, we've 2 gases on the right. So I'm going to have a decrease in S. So S is going to be, I predict, negative. Here I have 1 mole of gas, and now I have 2 moles of gas. So I'm predicting that we're going to have a positive S, an increase in S, an increase in entropy or disorder. Here we have 3 gas, we're going to 2 gas, so again I'm going to say a decrease in S, so it's going to be a negative value. So that's qualitative treatment of it. Now we've got to start doing our calculations. So you'll get a table like we have here when you're in the exam. Okay, and it has all the entropy values assigned to each of the substance. You note they're all positive, okay? You never have a negative entropy, you can't have a negative measure of disorder. Okay, so we'll flick over and we'll do these 3 questions on 3 separate pages here. You might want to, like I said, maybe listen to the first one and then pause the others. So how do we do this? Well, we go to our table and we find our entropy values for each of our reactants and products. We have to remember that those are in kilojoules per mole, and we must multiply up by the reaction coefficient, so 3 and 2 here in other words. And then we simply remember to do products minus reactants. You'd be amazed how many people do it the wrong way around. And we get minus 198. And that's what we said earlier. We thought we would get a decrease in entropy, and that's exactly what we had. Don't forget your units. Okay. Now you might want to pause the video here, or maybe even go back to the other one and get the values off the table and do it yourself. So again, we have to remember our 240, okay, on the right hand side here, okay, is going to need to be multiplied up by 2, of course, and then it's a very simple matter. And again, we said we would have an increase in entropy here, and we do have an increase in entropy going from 1 mole of gas up to 2 moles of gas. So we're just sort of always estimating is our answer actually correct each time. Okay, let's look at the final one then. I'll skip through this one relatively quickly. We should be getting the hang of these by now. Okay, so again, we just pop our little reaction coefficient numbers on. Make sure we multiply it. Make sure we do it products minus reactants, not the wrong way around. And again, we said we were going 3 moles of gas to 2 moles of gas, giving us a negative or a decrease in entropy. And that's exactly what we've got. Again, put your units on. Okay, so we have a few here. So I'd like you to pause the video now, guys, and see if you can have a go at those 3 questions there. Okay, and when you're finished, then I will, or whenever you start the video again, sorry, I will put the answers on the screen so that you can make sure that you are correct. But the principle behind them is exactly the same as what I've done on the previous, and you've got all the information down below. Just be aware, guys, that the number that comes after it is the number relative to the compound. Okay, a few people have done this before and have maybe done something like used 152 for the oxygen, which is not right. Okay, so pause the video and have a go at these, please. Okay, so the first one, the entropy in the products, you should have had a value of 509.2 minus 266.2, giving you an overall energy or an overall entropy change, sorry, of 243. Okay, in fact it's just 243. Okay, the next one with the iron, then you should have had 146.4 minus 491.9. Okay, giving you minus 345.5. Okay, and again, you should be sort of treating these qualitatively, making sure that you know that your answer is right or wrong, if it's positive or negative. All right. So if you do get if you do expect it to be positive and you get a negative answer, well then you maybe go back and check it again. So the last one is 631.1 minus 303.5, and that gives us a positive one again, and it's 327.6. Let's just check qualitatively that we would be on the right side. So we have two solids, we've got a gas here, so we're expecting a positive value, which is what we got in part A, so that's fine. Part B, we have three solids, two gases going to one solid. I'd expect a big decrease in that second one, and we got minus 345, which is sort of concurs with what I would have thought. Here we've one solid, two solids going to one solid, and two gases and a liquid, so I'm expecting a big increase, so I get positive 327. So that's fine. I think we're pretty much spot on there. Okay, so that's your entropy. That's how you work out entropy. That's how you treat it qualitatively. That's how you treat it quantitatively, and that's how you work out your entropy change. Now we're going to look at working out what's called the deltaG, or the Gibbs free energy, and now we take into account both our deltaH and our deltaS, which we've just spent some time working out. Now here's the bad news. deltaH is covered in AS2, as well as your Born-Haber stuff that you did earlier in this year. AS2, you've been able to work out deltaH by Q equals mc delta T over the number of moles, or you've also used your bond enthalpy calculations, or you've also used your Hess's law. Now those three skills or areas of learning still apply in A2. Okay, so you will be asked to work out these reactions or these deltaH's. You just won't be given the deltaH. You'll have to work them out using those three areas of learning from AS2. So make sure you know them. Okay. The the T value is in kelvins. So if it is given you in degrees Celsius, it's degrees Celsius plus 273. Okay, and to turn it into kelvins. Okay, you can't have a negative Kelvin, by the way. The lowest it goes is 0, and that's important for some things we do later. And the last thing that I would say is the delta S. Remember, it has to be turned into kilojoules now, so you're going to have to divide your delta S by 1,000 before you start doing your calculation. Very simple to divide it by 1,000 in your head. That before you start would be my advice to you. Okay. Right, so this is called the Gibbs free energy. Okay, and this is what we use to actually indicate whether a reaction is or is not spontaneous. And if it's negative, we say it's spontaneous. If it's positive, we say that it isn't spontaneous at that temperature. It may happen at a different temperature, but not at that one. And that's pretty much our rule of thumb for A level. Okay, sorry, I should have said you might want to copy down that equation on the board, and in fact both those things in the pale brown box is quite useful. So calculating it, really, I've kind of covered everything that I said. In this slide we talked about the delta S being turned into joules, and that would require you to divide that term by 1,000, okay, to get it into kilojoules. Right, so let's have a look at a question here. So I'll do the first one. You might want to pause the video perhaps and do the second one. Okay, so we have been given here our delta S values. We actually worked them out in a question previous, but we haven't been given our delta H values. So we're going to try and work out our delta G by using delta H minus T delta S. Now, we've been given enthalpies of formation. You can see that here. And for those of you who can remember from last year, the enthalpy of a reaction is equal to the sum of the deltaH formation of the products minus the sum of the deltaH formation of the reactants. Okay, so we've got to do that. So let's look at the first one. Well, there is no enthalpy of formation of nitrogen and hydrogen because the enthalpy of formation deals with the change of a substance from its elements in their standard states to that substance. Well, nitrogen and hydrogen are already in their standard states. So for the reactants, if you like, a bit pointless, but it's 0 plus 0. For the products, we've got ammonia, but remember we have two ammonias, so it's 2 times 46, so it's actually minus 92. So the enthalpy of reaction in this case is minus 92. Okay, so our delta G calculation is minus 92 minus our temperature is in the question and it's given to us in Kelvin, so we don't need to do anything to it, multiplied by our delta S, which is up here. But remember, that has to be divided by 1000. Okay, and that will give us our delta G value. I'll just clear the board here because this is done for us. Okay, there we go. So you can see all the terms I talked about. That was the delta H. Okay, you can see I divided my entropy by 1000 there. You can see I put in my kelvins there, and that tells me that the reaction is feasible because it's negative. So maybe you want to pause the video now and have a go at part B here with the carbon monoxide turning into carbon dioxide. So I'll start it in 3 seconds. 3, 2, 1. Okay, so our delta H is again sum of the enthalpy of the products minus the sum of the enthalpy formation of the reactants. Again, you can see there's a 0 here, which is because we have one element in its standard state, oxygen. And we get that for our delta H. Our delta S, we remember to divide by 1000. Our temperature is 298 kelvins. Okay. And we've got minus, excuse me, minus 514. So that's a very feasible reaction. Okay, now we're going to look at how do we actually work out qualitatively now the delta G to say whether it's positive, negative, and predict whether a reaction is or is not feasible or spontaneous based on these, just whether we know if the delta H is negative or the delta S is negative or positive or vice versa. Okay, so we don't have any actual numbers here. So we want this to be negative for the reaction to occur. This is already negative. My delta S is positive, but remember it's this term here, then that term must be negative. So everything is negative on the right, so this reaction delta G is always going to be negative. So it's going to be feasible and spontaneous no matter what the temperature. So that reaction will occur at all temperatures. It's not temperature dependent at all. Let's look at this one. So we have again an exothermic reaction. We have a negative delta S, which means this term here is going to be positive. So what we don't want is this term to be too positive. And if we don't want it to be too positive, because the more positive it is, the more likely it is to override the negativity of the delta H, if you like. So therefore, the lower the temperature is, the more chances it is that the delta G would remain negative. So this is a reaction that would occur at low temperatures, or spontaneously at low temperatures. Now from an industrial perspective, that's not ideal, okay, for the simple reason that low temperatures equals low rate. So this is where catalysts come into play, and that you try to use a catalyst to allow you to still get a decent rate of reaction at lower temperatures and allow you to get a good yield as well as a good rate. Okay, let's have a look at this one. Then we have positive and positive. So how are we going to get our delta G to be negative this time? So that term is positive, meaning that that whole term is negative. So I want this to be more negative than that's positive. So the bigger the T is, the more negative that the minus T delta S will be. So this time we're going to run this at high temperatures. So the higher the temperature, the more likely delta G is to be negative, and therefore the more spontaneous the reaction would be. So it has to be high temperatures for that one. This one, we have positive and we have we have negative for that, which means this term here is also positive. So we've all positivity on this side, so delta G can only ever be positive. It's never going to be negative, so this reaction won't happen no matter what the temperature is. It is not going to be spontaneous. There aren't any actual reactions like this in the world, but it's one that you might be asked about in an exam nonetheless. Right, very quickly, the magnitude of delta G. So our rule of thumb is that below zero it happens, above zero it doesn't happen. It doesn't happen. If it's below minus 60, we assume that reaction goes to total completion. But there is a caveat there. That may not happen. And your reason for that not happening is because the activation energy for that particular reaction simply might be too high. So please bear that in mind when you get asked a question where delta G is negative but the reaction doesn't happen. That's because of a high activation energy. If it's above 60, we simply say the reaction just full stop does not occur. Between 0 and 60, you're into your equilibrium reactions where they lie closer to the left hand side than the right hand side, so closer to reactants in other words. And then between minus 60 and 0, that is again equilibrium but lying towards the right hand side towards products. Bullet point 1 on that slide is probably the only one that's relevant to you at A level. I wouldn't worry too much about 2, 3 and 4. Right, the next thing that you might be asked, so we've done 2 formulas so far. This is the formula number 3 on this slide, and you'll have a 4th formula on the next slide over. So we have to work out, well, what temperature does a reaction become feasible? We've already looked at some reactions today where we have a positive delta G, so we say the reaction is not feasible. But can we work out what temperature it does become feasible? In other words, at what point does delta G become less than 0, become negative? So we have to rearrange our equation that we talked about earlier. Okay, so we want to find out where that value on the left, that delta G value is 0, and to rearrange that, we simply do delta H equals delta S. Now remember, again, I'll keep going on about this, the delta S needs to be put into kilojoules. Okay, and that's very simply it. So we'll have a look at a couple of examples like this. Okay, now if the reaction happens to be endothermic, your answer to that question is that the reaction becomes feasible above that temperature, and if it is exothermic, it becomes feasible below that temperature of feasibility that you've worked out. The final formula, so you might want to copy that formula down into a piece of paper because you're going to be using it to do some questions. So I'll move on in a minute. Okay, so the final formula this time is to work out at what temperature is a reaction actually occurring. So the last formula allowed us to work out at what temperature does a reaction become feasible. This time the reaction is actually happening, but we've got to work out what temperature. Okay, so that is delta H minus delta G over the delta S in kilojoules. So again, a very important formula. Copy it down, make sure you learnt it. Okay, so I'll just put this summary slide up and you can pause the video and read it. I'm not going to go over it because I've already spoken about everything that's on this slide. Right, so we've got a few calculations to do here. Alright, so we're getting into some calculations. So what I want you to do is to pause the video, okay, do them, and the answers will come up on the following slides. Okay, so pause that video please. Okay, so problem 7, okay, was very simple really. They give you the delta H and the delta S. The only thing you really had to remember to do was to, first of all, do it correctly on your calculator. Sometimes people, especially when they're dividing by 1,000, they tend to work out this whole thing here and then accidentally divide that by 1,000. So make sure your calculator skills are up to it. So that's minus 257. That's a feasible reaction at that stage. Down here then we were doing something similar, okay, and we worked out that the reaction wasn't feasible at 1,000 kelvins, but it was feasible at 1,500 kelvins. Those are your two delta G values, by the way. Then the next question asks us what temperatures does it become feasible. Now, if you're on the ball, you will realize that the temperature has to be between 1,000 and 1,500. So that's where your answer should lie. And again, we're into delta H over delta S in kilojoules is all we had to do, and it comes out at 1,248 kelvins, which is of course between the two values above where we worked out one was feasible and one wasn't feasible. Okay, so there's 3 more questions. This time you have been given delta H of formation, so you're going to have to work out the delta H of the reactions in each case using a little Hess's law. Remember, delta H of a reaction equals, for when you're given formation, it's the sum of the delta H formation of the products minus the sum of the delta H formation of the reactants. Okay, so again, you'll notice up here you have 2 zero values for elements in their standard states, and in the next question you have 1 zero value for an element in its standard state. So I will, if you pause the video, if you want to do those 3 questions, okay, lay all your working out really well so that you can find out if you did go wrong, where you went wrong on the next page. So the answers are coming up on the next couple of slides, okay? So pause the video now, have a go at them. So that's the answer to the first part. You can see there's your delta H that you've worked out. Okay, you've then worked out your entropy, okay, or your entropy change I should say, as that. Remember that you have to divide that down by 1000, and you got your delta G here to be a feasible reaction. Question 10 then, okay, so your temperature, your final temperature I don't have on there, it's an endothermic reaction, so it has to be bigger than 960 kelvins. That's your answer. So your delta H is there, your entropy change you get there, your delta G value was there, and then you did your excuse me, your delta H divided by delta S over 1000 to give you your 900 or greater than 960 kelvins. Okay, question 11 then, I'll leave that up there, you can read your way through that. Hopefully you were able to work out. So the answer to the first one is C, the answer is, next one is D, the next one is A, and the final one is B. Okay, with explanations there as well. Okay, so again there's another one. I would advise you to pause the video and then I'll move on. So I'll move on in 3 seconds. Okay, so those are the answers. Again, pause the video, I'll move on in 3 seconds. Okay, so there's another question. Pause the video. Okay, and those are the answers. So you might want to pause the video, check that. I'll move on again in 3 seconds. Multiple choice question. Pause the video. That's your answer, and that's the calculation, the way to do it. Very simple one. Okay, again, pause the video. You've got a little equation to write here this time, so you might want to go and read up on your how does a sodium hydrogen carbonate react with certain functional groups. Okay, you might hopefully notice that there's 3 carboxylic acid groups in here. That's what the sodium carbonate reacts with. It doesn't react with an OH alcohol. That's an alcohol group, remember, different from a carboxylic acid, so it won't react with that. Okay, and that's your answer. So you can see loads and loads of gas produced here, water produced here. That, okay, is solid, and that possibly a solid as well. Not quite sure, but anyway, one of them might be. Doesn't tell us actually. That might be liquid. But anyway, you're making huge amounts of gas over on the right hand side, so it's a very positive delta S. So we'll move on in 3 seconds again. Okay, another multiple choice. Move on in 3 seconds. Alright. Okay, so as long as you remember to divide your delta S by 1,000, the other trip in there was that was not in Kelvin, so you had to add 273 to the degree Celsius to get it into kelvins. Move on in 3 seconds. Okay, so this time you've got to work out your delta H again. You've got your delta HFs given to you, so I'll very quickly remind you, although I think I've told you enough, is the sum of the delta HFs of products minus the sum of the delta HF of the reactants. Okay, so again, pause the video. I'm moving on in 3 seconds. There's your answers. Okay, so there's the first answer, second answer, third answer. Okay, moving on in 3 seconds. This follows on from the previous part of the question, so you need to look at your answers to that. Pause the video. Okay, moving on in 3 seconds. Couple of little multiple choices. Okay, moving on in 3 seconds. There's your answers. Hopefully explained in enough detail for you to see. Pause the video. Okay, here's the next question. You've got to work out the delta S in this instance. It's not given. You've got delta G and you've got delta H this time. So remember, this time I ask you to calculate the temperature at which the reaction is occurring, not the minimum temperature. So remember, that is a different temperature. That's your delta H minus your delta G, over your, goodness me, delta S in kilojoules this time. Okay, I'll write that out over here because that is, so the temperature this time, that the reaction is actually happening. Okay, remember that last formula if you can remember from the PowerPoint. Sorry, so I'll move on in 3 seconds. So there's your answer, 323.7 kelvins. Probably should have wrote that to 3 significant figures at 324 actually, guys, because I noticed just up here we're working on 3 SF. 324 kelvins, probably the answer I should give. Okay, so pause the video. Okay, you've got a Born-Haber calculation to do up here, so a bit of revision over your Born-Haber stuff. Pause the video. Okay, go. Some people down here forget to multiply by 2 for the 2 chlorides. Don't forget that. Yeah, calcium chloride is CaCl2. Okay, so pause the video. Okay, so pause the video. I think that one's fairly self-explanatory. Okay, so pause the video again. Okay, pause the video. Okay, that's the last slide, guys. Right, so hopefully that's give you an explanation of what entropy and the Gibbs free energy is, and give you a good idea of the how to do the calculation. Lots of calculations in your textbook and the past paper question book that you'll be given as well. Okay, so hopefully that clears that all up. Any problems, you can obviously come and see me.